One sec here. Setting up the meeting right now. Awesome. The live stream is up. Hey everyone, and I'm gonna record this meeting. Alrighty. Hey everyone, welcome to the Splunk Virtualized Systems Meetup, and I'm your host Masaka. It's been a while since we met since the last time because I had a long break, a long vacation. I traveled back to South Korea for a fun trip and then to my hometown to visit my family. Now I'm back, I'm refreshed. And today it's my big pleasure to introduce you all Alex Crichton. He's a software engineer at Fermion, a core maintainer of a Wasm runtime, Wasm, and previously he has a core team of Rust programming language. Alex is a very proliferate engineer. He has done a tremendous amount of work on Wasm and the Rust ecosystem. And today, he's here to talk about the virtualization and WebAssembly. Before we begin, I want to ask you all to abide by our code of conduct. Basically says to be nice and respectful to each other. Just be a nice human being, folks. If you have any questions or comments, please use the raise hands feature on Zoom, or you can comment them in the chat, and I will be monitoring all the chat messages for Alex. All right. Without further ado, Alex, I'm handing the stage to you now.
Sounds good. Let me do the share screen thing again. All right. Does everyone see that okay? Perfect. Thank you so much, Masaka. I don't really have much to introduce myself otherwise, so I'll dive right into it. Hello, everyone. So I am going to talk about virtualization and WebAssembly today. So Masaka invited me to talk a little bit about sort of kind of how WebAssembly can fit in sort of a container style or VM style ecosystem, kind of how these two technologies relate, and just kind of give a background on some other custom stuff and playing around with towards the end. So I think I'll start off by saying I am not an expert on virtual machines or containers by any means. So if anyone wants to raise their hand and correct me for anything, please do. I'd be more than happy to update things here. I know much more about the Wasm side of things than the container side of things. But to sort of start this off, I want to sort of give at least my own personal understanding of containers and VMs and sort of some of the benefits and some of the downsides of containers and VMs. And we'll see how Wasm kind of plays into this a little bit as well. So it's kind of one of the main benefits of containers and VMs, primarily virtual machines, is that they have a very, very strong security story. They're very, very widely used for running untrusted code. This is just like Google Cloud, Amazon Cloud, Azure, all the cloud providers, everyone runs virtual machines. And the really nice thing about this is that they actually run all native code at native speeds because you run directly on a CPU, you get all CPU features you need to, or at least most of them. Most of them you need for speed. And then there's a nice suite of kind of standardized tooling. So most folks use in Docker, Kubernetes, or various kind of things around like OCI and stuff like that. So it's a generally standard ecosystem. And if your software currently runs in Linux on your local machine, it's probably going to run inside of a container. I know there's stuff, virtual machines you can run, I mean, Windows, Mac OS, and all that stuff, but it's kind of like containers at least are much more bound to Linux. Some of the major downsides, though, of containers are that virtual machines can be very large. So they can be multiple gigabytes in size for disk images and all that fun stuff. It can be a very long time to boot them up relative to they weren't running to now they are running and they're ready to handle requests or whatnot. You have to do things per architecture. You can't just build one thing for one machine. You have to kind of have a couple of different ones. And then finally, if you want two VMs to talk to each other, you often have to go over the network. You have to go on like have various sort of orchestrations and things. It's not always the fastest thing necessary. So in this sense, I want to kind of contrast this to the WebAssembly side of things. So I realize that many of you are sort of probably very new to WebAssembly, or maybe have not heard much about WebAssembly. So I'll go briefly over the overview and I'll kind of dive more into WebAssembly a little bit. So at a high level, WebAssembly retains a lot of the benefits that containers have. So WebAssembly has a very, very strong security isolation story. It has, it can generally run things at native speeds. There's a few caveats to that, which is why there's a bit of a gray check mark. I'll talk a little bit more about that later. And for standard infrastructure and tooling, you can kind of expect a lot of languages nowadays to have support for WebAssembly. So this is kind of C, C++, Rust. You can even find Python and JavaScript, kind of a lot of standard languages. I'll tell you more about that later, but they kind of like their standard build tooling will all mesh into WebAssembly well. The major downside, however, is that WebAssembly does not support most existing software for Linux, with a bit of an asterisk. So like if you're kind of using fancy kernel APIs, it probably doesn't work quite just yet. So it's a bit of a portability hazard there. However, the nice part of WebAssembly is that it doesn't have any of these downsides. WebAssembly can be a very, very small module. You can run it very, very quickly from it doesn't exist to now you're up and running very, very fast, much faster than a virtual machine, for example. It is portable, so it's no longer specific for architecture. And I'll talk more about the communication aspect as well. That's sort of like a taste of what's going to happen here. But before I go to kind of give you an idea of kind of what this all is, I want to first give you a little bit of a heads up or kind of a bit of an intro as to what WebAssembly is at all. So WebAssembly is I'll use these words of safe, portable, and low-level format. And the idea is it's intended for the web, but it's not exclusively made for the web. This is one where, despite the name, it has seen a lot of growth and a lot of usage off the web, kind of in this container and virtual machine space, or kind of the outer browser use case space. That's at least where I personally primarily work on the Wasm time runtime. And then the other main thing about WebAssembly is that it is an open standard developed by a standards body. So this is not just one company doing something. It's not just one person sitting off in the middle of nowhere designing something. It's a standard agreed upon by many big companies. All the major browsers are kind of the primary stakeholders right now, and they all kind of march the WebAssembly standard forward and add new features over time. So just to dive in a little bit of this safe, portable, and low level, I can kind of expand and say that from the safe side of things, this is where a module, WebAssembly module, which is a binary, it always executes in a sandboxed environment. So the idea is that no matter what happens inside there, it's all nice and self-contained, kind of like a virtual machine in that regard, where whatever the guest does, you have very well defined. You can shut it all down if you want. You can kind of move it around if you want, things like that. And a big part of that is that all I/O is not inherent to Wasm, but rather done through function imports. So you explicitly say, I would like to import the function to print to the screen, things like that. And then kind of on the more academic side of things, WebAssembly is a formally proven safe specification. I believe this in terms of the sound. So the WebAssembly type system is formally proven sound of all the execution semantics within. Oops. This portable side of things is that it's not tied to x86 or ARM64 or anything like that. It is portable across all ISAs. So it's a new ISA effectively, which then gets compiled by compilers to your own native architecture. But the distribution artifact is not these native binaries, rather it's the WebAssembly module itself. And so this way, it's no one programming language is supposed to work. No one particular programming language or model is supposed to work. You can run it in a browser, out of a browser, on very small devices, very big devices. You can kind of run it a whole suite of locations in that regard. So you have a lot of flexibility in terms of where your Wasm is running and how it's actually run in various environments. Also, you can do lots of fun transformations like put little probe hooks, kind of make things or kind of add more checks or debug checks, all that fun stuff. And this aspect of low level of like kind of all these ideas sound like a nice, safe, like garbage collected language, but the idea is intended to be that Wasm is running at roughly near native speeds. So the idea here is you're intended to take WebAssembly and compile it to native code, either in a just-in-time fashion or ahead of time fashion, depending on how your setup is going to work. And then being derivative of the web, the binary size is a very important aspect. So the idea is these actual Wasm binaries are intended to be as small as possible because you'll be sending them over the web when you're visiting web pages, and especially once you start applying like gzip compression or any other compression algorithm, these things will get even smaller. So this is sort of a kind of minimal example of a WebAssembly module. And if you're not familiar with Lisp or kind of S expressions, that's this term for parentheses all over the place. So that's sort of the textual format for WebAssembly, not the binary format, but this is just so we as humans can take a look at it, sort of like assembly for native platforms, but a little bit different because this describes the entire module. So we can see here that WebAssembly code is organized into particular modules. They themselves can have functions, which we see here. They can also have memories and globals, so we can see more later. And the actual kind of internals of the instructions here, it's based on a stack-based virtual machine. So there's no registers, there's no kind of native instructions or anything like that. The idea here is you sort of have an empty stack. You push the first parameter, which is local 0, push the second parameter, and then the add instruction will pop two things and push the return value. And I forgot to type the return value here, so we can fix that later. But the primitive types you have are not intended for high-level languages. This is just a 32-bit 64-bit integer and a 32-bit 64-bit float. There are some others as well nowadays, but kind of for many languages, this is the suite of types. This is very much intended to be a compilation target. You typically don't write this by hand, and so what you would actually do, you would write some Rust code, you can then run the Rust compiler, and there are targets baked into the Rust compiler. We say I like to generate stuff for Wasm, and out pops a foo.wasm, which is if you take a look at it, it's got this kind of version header and everything. And then you could take this and run it directly inside of a WebAssembly runtime. So, for example, this here is Wasm time. You can see when you run it, it actually prints things out. So this is obviously quite a lot going on here, and I'm not going to go too much into the details of WebAssembly here, but I can always answer questions as well. But the general idea is that there's lots of different languages that support WebAssembly. So I think all of these languages here have a port or at least a fork or work towards upstream to getting it supported to kind of more officially, if it's not already officially supported. So the idea is that this is kind of, or rather, WebAssembly, I think, truly is actually fulfilling its original intentions of supporting a wide variety of languages, as we've seen more and more languages start to port and kind of see the benefits of running in either on the web, off the web, various places like that. So I don't want to go too deep into the details of WebAssembly, but I do want to open it a little bit to kind of show you at least the high level idea. So we can take this foo.wasm and we can convert it to its textual form. So the actual Rust compiler would generate this Wasm binary, but we'll take a look at the text. There's a whole bunch of constructs here. We got types, imports, functions, blah, blah, blah. There's lots of stuff omitted here. But the main thing that I wanted to give you a kind of a peek at is this idea of this import. So I told you that Wasm doesn't have any IO capabilities. It can't print to the screen, for example. And so this is the function where you say print to a screen. So this is where it gets to introduce something called WASI. So WASI stands for the WebAssembly System Interface, and it is intended to sort of fill in this hole of Wasm doesn't have I/O, but WASI can provide I/O. So when you're running in a browser, you've got this entire JavaScript runtime, you've got the entire browser ecosystem, the entire browser platform, but outside of a web browser where I primarily work, and none of that exists. And so WASI is this kind of filling in the gap where it's a standard set of imports that you're able to import, kind of looks kind of POSIX-like, and it's all designed similar to WebAssembly in terms of it's supposed to be portable across many platforms, including the web, safe in terms of makes it not very error prone by default, but also efficient at the same time. So this all started historically with what we now call WASI P1. There's a few other names for this, whether we kind of figured out what to call this over time, but the idea is that this was sort of originally derived from POSIX and Cloud ABI. And the idea there was a lot of capability-based security, a lot of kind of POSIX looking functions. And so you might see references to this, but this is the idea of kind of what was originally done. A lot of existing languages do have support for this, but this is sort of kind of considered the historical version at this point. So this is sort of the P1, but there is a P2, which is sort of the newer version of this, or kind of what the WASI group is now working on today. So this is all based on something called a component model, and the IDL now is called WIT as opposed to WITX. And again, I'm kind of glossing over quite a few details here, but the general idea is that this is now intended to be sort of a modular set of interfaces. I've got a whole bunch listed here, such as IO, which is you input output streams. You've got random for kind of either cryptographically secure or random number generators or just pseudo random number generators, sockets for TCP, things like that. These are modular in the sense that, for example, on the web browser, you don't have TCP and UDP, but you do have random. And you do have HTTP both on the CLI and the web browser, but it's implemented in a very different way in the web browser, where like on the CLI, you might have like sockets and things like that. So this is intended where there's a couple of set of standard worlds. So we have the WASI CLI world, which is intended for I'm going to run this outside of a browser, and that's got all these things available to import. They're all implemented with kind of native Windows, Linux, macOS APIs, things like that. And then you have two major worlds, or sorry. The other world is HTTP proxy, which is the idea of you can define a WebAssembly module where it takes a request, gives you a response, and you can reuse that if you want. But the idea is it's got one function, which is take a request, return a response, and it's very geared towards HTTP. It, for example, does not have the CLI interfaces. It does not have sockets. It doesn't have a file system. It's intended to kind of be I would think like Nginx, like you run it next to an Nginx server or something like that, kind of your function as a service style of things. Now, I will go a little bit to the component model just sort of at a high level, where the idea is that this is a layered thing around core WebAssembly, what we're calling. So what we saw earlier was this core WebAssembly module, and the component model wraps this. And where I was saying in WebAssembly, you only have I32 and I64, a component model gives you a much richer set of types to work with. So you get strings and records and variants and enums and kind of all these fun things, which is kind of much more closer to sort of a IDL or like kind of like Thrift or protobuf, things like that. And the idea is it makes it much kind of easier to communicate between a host and a guest, where on the web, for example, you'd probably have a lot of JavaScript glue saying this integer corresponds to this string, kind of all that fancy stuff, but we don't have that in the out-of-browser use case. So this is a standard set of meanings to what all these little I32s are running around the core module. They're actually strings when you talk to the host and things like that. So this is all what WASM-2 is based on, and this is sort of the way that all APIs are defined. So this standardizes on that glue that I was talking about with JavaScript, where we do actually generate that for when you run a component on the web right now, but the idea is you don't need that off the web. And in theory, eventually one day the web might actually have native support for components where you wouldn't need any of that JavaScript glue. So just to give you a brief example of components, we can take the exact same source code as before, but we'll change a few things of that. Previously, we compiled for this P1 target. We'll switch that to P2. We can see the version number came out a little bit differently just because the binary representation is slightly different. If you actually look inside here, you'll find the exact same core module inside here with some extra wrapper stuff. And that wrapper stuff looks a little bit like this, where the idea is instead of a module top layer, it's a component top layer. And then we have these WASI things, which look like WASI P2. So we're importing an instance of the environment CLI interface. We're exporting the run interface kind of. This is all intended to be just, it's similar-ish in functionality to WASI P1, but it's much higher level in terms of it's much easier for hosts to interact with, embedders to interact with, and all that fun stuff. So, all right, that was my whirlwind tour in 15 minutes to WebAssembly. So I want to pause here. Does anyone have any questions about WebAssembly? I can go back and otherwise I can go forward and talk about virtual machines and WebAssembly. So any questions? All right. I'm assuming you're all WebAssembly experts now, so I'll move on. No, just kidding. So now that we all have a bit of an introduction to WebAssembly, I want to talk a little bit more about kind of comparing and contrasting virtual machines and WebAssembly and the two technologies and kind of on these points that I was talking about earlier. So the first thing I'm going to talk about is security. So I was saying that virtual machines are very battle tested, are very well known isolation security boundary, and that's sort of like the industry standard today of running untrusted code. WebAssembly does offer, however, that it is a formally proven sound language. It is a formal semantics around it. It is known to be safe, and so that they sort of have similar things in that regard. The downside, one of the downsides of virtual machines, though, is that you have a very large hypervisor under the hood, which is known to have bugs every now and then. There are virtual machines escapes every now and then. And WebAssembly is not free of that either. WebAssembly is running inside of an engine which may or may not be bug-free. Most frequently is not bug-free. There are typically bugs here and there. And so there's a lot of, while WebAssembly is safe at a formal level, it may not be safe necessarily at a practical level, or rather, there are bugs to find and bugs that could possibly be exploited. Another thing is that virtual machines and containers have been used for decades. They've been used for the longest time. They've how everyone runs, and so they're very well understood, very well known. Everyone knows kind of what the security weaknesses are, whereas WebAssembly is a relatively new technology. So that doesn't necessarily mean that it's inherently secure. It just means that we haven't necessarily had the battle track record of people attacking it, people trying to exploit it, all that fun stuff. But an interesting aspect of the security aspects here is that the technical constraints of virtual machines, they're big. They take a long time to start. They sort of guide how you run virtual machines. So you might run a server in a virtual machine, the entire server. So every single request hits the exact same server. Everything's in process, and you just sort of rely on the server being correct to not leak information between requests. Whereas with WebAssembly, the performance profile of WebAssembly effectively unlocks a brand new paradigm over you couldn't even do this before with virtual machines because it'd be way too slow, at least in theory, that you could have a WebAssembly instance run for every single HTTP request that you receive. So every single request you get to your backend is a brand new instance, pristine, zero leakage, and you have an extra security layer that way in terms of you can make sure that nothing leaks between them, because by construction, you're destroying the entire sandbox and bringing it back up on every single request. I'll go a little bit more into the performance aspects later, but that's sort of like the idea of what WebAssembly can unlock. So on the speed aspect, virtual machines definitely have a huge leg up here. This is one where you're running entire operating systems inside of a virtual machine. They have raw access to the entire system, or rather what's been virtualized, but they've been optimized and worked on for decades at this point. So you have near native speeds, you get all the SIMD features you want, you get as many threads as you want, configure that you can have. So there's effectively no overhead with running with virtual machines in that regard, at least for the predominant use case scenarios. This is one where it's not necessarily everything will run exactly the same speed, but that's the general idea. WebAssembly, however, is a virtual runtime. And so the idea is that it's a native, a virtual ISA, which you'll compile and then run as actual native code, but it does tend to run a little bit slower. Because of the sandboxing technologies, you tend to expect around a 15 to 20% performance overhead. So whether or not that is acceptable kind of depends on the use case, but I'll let you go.
We got a question in the chat where Harry asked, what if I want to share, how about performance of starting a new sandbox? I guess he's asking when you talked about having Wasm starts per request.
An excellent question. Also, I have now opened the chat, so I can also see it. Thank you. But starting a new sandbox will depend on the specific runtime. But in WebAssembly, at least in Wasm time, you can start a sandbox in microseconds typically. So this is you can do some kind of pre-computation to get it ready, but actually starting from nothing and then tearing it down can take is on the scale of microseconds. And then the question of what do you want to share state between requests? Should I share state between requests like a game server? So yes, that is definitely possible. This is one where if your server requires it, as many do, there's no reason you have to tear down an instance or kind of bring up an instance on every single request. As very much within like the actual application itself. It's more of most people didn't even think this was possible ahead of time, whereas now it is much more towards the realm of technical feasibility. So definitely both are enabled, and it's one where the traditional style still works just as fine. It's just you can do a little bit more as well by having isolated between if you have some sort of backend data elsewhere. Can you have a leak? Yeah, you can definitely leak memory, but it's sort of just kind of like native code. You can leak code on a native server, and you can also leak code in WebAssembly. It's kind of where WebAssembly is not a rigorous, safe language per se. It's more of like kind of a C layer where you can make all the mistakes. You can have use after freeze, you can have double freeze, you can have leaks, you can kind of all the stuff inside of WebAssembly. But the main aspect is it doesn't impact the host. So the host still has strict control of whatever you do inside of WebAssembly. You're not going to leak on the host, assuming the host is implemented correctly. Whatever you like out of control, out of memory, infinite loops you have, the host can stop you at any time, can axe you at any time. If you ever ask for more memory, the host is always interposing, saying, you want 10 gigs of memory, but I only give you 128 megs. So I'm going to say, no, you can't get 10 gigs of memory. So that's sort of the virtualization aspect, of the host has complete control over these knobs and saying it can always deny resources to WebAssembly as it wants. I'll pause here. Any other questions, or did I answer those? Any further questions? Did I answer everything? All right. So continuing on the speed side for WebAssembly, so as a virtual instruction set, means that it's not x86, it's not ARM, which means if x86 adds a brand new feature, that's not in WebAssembly. And so this does need extension over time, and this is happening. So the WebAssembly community group kind of released the MVP, is what is called the WebAssembly kind of the 1.0, I think it was 2016. And then since then, it's been iterated on, and many more features have been added. It's like SIMD, threads. What are some other big ones? Like memory copies and things like that. Anyway, a lot of various kind of miscellaneous things. Oh, exceptions is a big one. But anyway, miscellaneous things are being added to WebAssembly, but they do take a lot of effort to add in a standard fashion. I can also definitely say that so threads on the threading aspect of WebAssembly, threads do work. It's a little weird though. It's a little kind of it takes a lot of work. It takes a lot of like you need a lot of investment to get threads working, and I won't go too much into it here, but it's definitely not a it's not a turnkey solution like it is on native platforms. You can't just take pthread, spawn a thread, and have it work just fine. It will work sometimes, but there's various caveats, things like that. Read the chat here. We know Socket is a part of WASI-P2 spec, but it is still not a full version. When can we expect a fully functional version of Sockets and networking to work with WASI so that we can start porting most of the cloud-based apps? So this is one where P2, well, working WebAssembly takes time. We're working things as fast as we can, and so this is one where the intention is that the current WASI and socket support or package has a lot of what's necessary for a lot of TCP and UDP things, kind of more of the maybe 80%, 85% use case. Some of the more niche cases aren't necessarily fleshed out yet. So we've been kind of getting that forward, getting runtimes on board, getting ecosystems transition from P1 to P2, and the intention is that it's much easier to add more extensions over time to networking. So our thinking is we wanted to kind of get the base set in there, and then kind of, in theory, kind of what you say is most cloud-based applications. We do want to get those working, and that's sort of the theory, is that what's there is there. If there is stuff missing, I would love to chat about that, and we can all, because WASI is definitely an iterative process, just like WebAssembly, and new features are being added to WASI as well. So, all right, any other final things on speed? I can also come back. All right. There's that. All right, so next thing I want to talk about is sort of the resources required. So this is where virtual machines are known to be a little heavy. This is where virtual machines can weigh up in gigabytes in size. Containers can be hundreds and hundreds of megabytes in size. Often you'll see this virtualized on the host with lots of processes, lots of threads, lots of things on the kernel side of things. So spinning one of these up is a big operation. It's got lots of stuff involved with it. And if you have the exact same virtual machine across many, many different places, it's often a lot of duplicating a lot of the things there. And so this is, or duplicating a lot of files, a lot of like kind of things resident in memory along those lines. And so this is one of the major aspects which WebAssembly is sort of a huge leg up on, where the idea is that where you might be able to take a server and run like 10 virtual machines, you in theory can run about 10,000 WebAssembly applications or WebAssembly modules inside of that exact same server. So the idea is that the per instance overhead of one particular WebAssembly instance is very, very small. So it's intended to be just constrained to exactly the resources and the memory footprint of the actual Wasm module itself. We can put thousands and thousands of these on a machine without really all that much overhead. The main limiting factor is honestly virtual memory. We kind of start running out of virtual memory when you actually run this many modules, but even that is tweakable. You can kind of change various settings if you're willing to accept more of a performance hit in that regard. And one of the nice things about WebAssembly is that we can use a lot of virtual memory tricks to make sure that if you have, I was talking earlier about kind of every request on a server gets in a brand new instance, you can have all the code for all of those is shared. It's only mapped in the module at precisely one location, but it's running simultaneously in dozens of different threads in various different points and things like that. So this is, from what I've seen, it's kind of 10x or more instances than VMs per host. But again, it's a bit of a apples to oranges comparison in the sense that a virtual machine is a full-fledged operating system. It's got a whole user space, got tons of programs inside of it, whereas a WebAssembly application is kind of more like one executable. So it sort of depends on kind of what you can fit within to kind of, if you can fit within sort of this one executable style, WebAssembly will allow you to kind of greatly reduce your resource costs, greatly reduce kind of the size of virtual machine or size of like servers and things like that. So, right, the standard tooling aspect that I was talking about later is sort of similar on both of these sides, in the sense that in virtual machines containers, a lot of folks are familiar with Kubernetes and Docker. There's a huge amount of blog posts about that. There's tons of documentation. This is very, very well known throughout the ecosystem. Even if you're brand new, like me, you can get up speed pretty easily in no time at all. WebAssembly is still coming along in terms of that kind of like very introductory documentation, but the idea is that most languages will have their own version. So example, Rust will have its own documentation for how to compile it to Rust. C++ would have its own documentation. Go, all these sorts of examples. From like a packaging side of things, this is where kind of the component binaries and the core WebAssembly binaries work pretty well, where they both serve as a relatively standard format that you can share around. I believe there's OCI specifications in the works for kind of connecting components to OCI and back and forth. So I think there's actually intended to be a lot of integration there in that regard. I'm not personally too heavily involved in that work, so I'm probably not the best person to ask questions about that, but I know it's at least progressing along. And one thing that is definitely I've seen kind of as an example is that there's a small set of libraries that are kind of like the core set of libraries in WebAssembly. And so one of the best examples of this is LLVM. LLVM is one of the primary code producers of from source code generate LLVM. So Rust, C++, TinyGo are all based on LLVM. It's also Swift, a .NET compiler. So that's sort of like kind of everything flows through there in terms of feature support or just kind of general support for features and standard tooling and things like that. So I do want to touch on this aspect as well, specifically porting existing code. And this is where virtual machines have a great story of like with a virtual machine, you might not even have to port anything because the idea of it's a machine. For containers, you probably need very little porting if you already run on Linux. And this is where you don't even have to have Linux once you have the whole virtual machine aspect. And so this is a very, very strong suit of the container side of things and the VM side of things. However, WebAssembly, as I've been saying, is a relatively new target, but it's not in existence before. So for example, if you only compile with GCC and you don't compile with Clang, you're not going to have a great time with WebAssembly because GCC does not have a WebAssembly backend just yet. You'll also find that a lot of applications will need source modifications to compile to WebAssembly. WebAssembly is not Unix, it's not POSIX, it's not macOS, it's not Windows, which most programs today, if they have some sort of system level stuff, they'll tend to assume I'm either on macOS or Linux or Windows, or kind of the general Unix family in that regard. But this is different from WebAssembly, and so you'll often need supporting like that. You'll often need to kind of upstream various aspects to upstream libraries. The good news, however, is that WebAssembly being a standard target, a lot of upstream authors are often very receptive to PRs. So if you want to implement WebAssembly, it's very rarely met with, oh, I don't even care about this. I would like to reject this feature. It's more of, oh, thank you. I would love to integrate this. Let's talk more about design, all that fun stuff. So that's sort of like at least a good side of things, but something to be aware of in terms of moving to WebAssembly. It will involve porting code. So I talked a little bit about binary size. Maybe I don't have to go too much over this a little bit here, but the idea is VMs and containers definitely very large. It's tough to kind of, this is the apples to oranges comparison where a virtual machine has an entire operating system inside of it, whereas a WebAssembly binary is just that one executable. But to give you a sense of scale, WebAssembly binaries can be as small as dozens of kilobytes, and they can also grow up to dozens or hundreds of megabytes as well, depending on the language runtime. So this very much depends on your language. So Rust and C, for example, can get down to very small dozens of kilobytes, but JavaScript, which brings an interpreter right now, like SpiderMonkey, tends to be on the more megabyte size of thing. But even that depends on the interpreter you bring. ClickJS is probably smaller. Various trade-offs to be made there. But just to give you an idea, WebAssembly is a range of size, is intended to range from very small up to very large. So I can talk a little bit more on the cold start here aspects here, where so virtual machines containers are not known for booting up quickly. This is where they've got a whole kernel sequence to boot through. The kernel's got tons of modules, and there's been tons of optimizations for this. I know Firecracker from Amazon is very, very heavily geared towards starting things up as fast as possible. And I have no doubt that it is the like pinnacle of the technology right now. And this is something that we very much wanted to preserve in WebAssembly. So WebAssembly was always intended to be designed for very, very fast instantiation times. Sort of the theory is that while you're downloading code on the web, so you visit a web page, it's got a Wasm binary, you're downloading that Wasm binary, your computer should be able to compile the WebAssembly faster than you can download it, such that the second it's done downloading, it's ready to go, which is on contrast with JavaScript, where you tend to have a lot more involved and a bit of a pause between when you're done downloading and you can actually run. But in any case, I can mostly say, at least from a high level, WebAssembly lends itself very, very well to running with a lot of virtual memory tricks, keeping things mapped in various places, resetting things very quickly. And the idea is that you can spin up an instance in a handful of microseconds, not milliseconds or seconds or anything like that. But that's sort of like a full multi-megabyte SpiderMonkey virtual machine starting up, doing a thing, and then tearing it down is a couple of microseconds. So this is sort of like the idea of this wasn't even possible before, so it kind of unlocks a lot of new interesting use cases for this sort of virtualization. Sorry, I think okay, I got a few more. I'll sort of go through these briefly because I want to get to the hypervisor side of things later. But portability side of things, I don't have to go too much here, but the idea is that virtual machines, you tend to have to build once per virtual machine. WebAssembly is a brand new architecture, which requires the porting I was mentioning earlier, but once you're running, you get to run anywhere on any server. Now, this, you still have to do performance testing in terms of you probably have an engine you're interested in, and you probably have an application you're interested in, so you run it on the engine, measure the performance, maybe, and you might still have to tweak code as a result, but yeah, let's see, is there anything else I want to talk about here? Yeah, the intention is that being a just-in-time compiler, or sort of being a virtual instruction format, you can kind of pre-compile this and say, I would like to run this on my phone, and I would also like to run this on my server. Both of those have very different chips, and so you can, for example, enable AVX512 to do lots of fancy stuff on the server, and it does less fancy stuff on the phone, which probably doesn't have AVX512. So, all right, the final thing that I want to talk about here in terms of comparing and contrasting, I was talking about this earlier, was cross-guest communications. This is where you have one virtual machine that wants to talk to another, a container wants to talk to another. A lot of times that's done today is with you sort of have Kubernetes to sort of align all the stars, get everything talking together. I've been told there's these things called like sidecars to make things route correctly, and you use a lot of JSON, a lot of serialization, a lot of protobufs, all that fancy stuff. So the idea is that's sort of the lingua franca with containers and VMs, and the intention is to improve a lot of that on WebAssembly. So I was talking with the component model, how we're talking at a much higher level. Like you can still talk about strings or records or variants and things like that, and you can talk or you kind of hop between one instance and another in as small as one function call. So you simply call a function, and the Wasm runtime can hop over switch instances very quickly. Does not require a lot of serialization, just kind of moving bytes from one place to another. But given the structured nature of the component model, it is intended to be that this is far faster than it is with virtual machines today. So, for example, if you have two microservices today that are kind of sitting off in a cloud talking to each other, you might be able to instead link those together into one WebAssembly binary and then run those right next to each other for various requests. And sort of this very fast startup time enables it to kind of all be nice and linked together. And then you get the speed benefits of whenever you call it, you don't actually incur a network round trip or anything like that. It's just kind of making a direct function call right there on the CPU. So that was a lot of words, and I don't expect everyone to remember all that, but I kind of wanted to kind of put this in a chart of sort of pros and cons of virtual machines and WebAssembly to kind of give you at least a high level overview of kind of the good parts and the bad parts. So virtual machines and containers, they've been used forever. They're very fast at native speeds, and they have a ton of support through Kubernetes, Docker, all that fun stuff. However, they're big, they take a long time to start up, and it's kind of hard to put lots of them on one machine. And you'll find these are sort of swapped for the WebAssembly side of things. So in WebAssembly, there are no cold starts. You can communicate very quickly between guests. You can put tons of guests on one machine, and you get this model of per request isolation. And there's a question of will there be cross runtime instances communication? If you mean cross runtime, can you elaborate on that? So by runtime, do you mean two different languages, like JavaScript talking to Ruby in Wasm? Or do you mean like one Wasm time server talking to like a different Wasm engine? Or just two different servers talking to each other kind of in the way that like virtual machines do today? Okay, that works just fine. I mean, that's in the sense of folks are probably not going to forsake their container and virtual machine infrastructure. And I'll talk a little bit about why in a second, but the idea is that you most likely use your kind of virtual machine infrastructure on top, and where you already have communication between these. There's no reason you can't do that with Wasm time, or you can't do that with various Wasm runtimes today. You could very easily say you can still make HTTP requests. You still have like a privileged API to sort of say I'd like to route this over there. So all that should definitely be possible. It's sort of more of giving you other possible alternative solutions to problems if you do have them. So I have another question of, is the additional implementation for features part of a higher level language compiler without the need to extend WebAssembly language of the engine? It depends. So there's a bit of a wall that's hit eventually. So there are certainly some higher level language features which you can implement in your compiler in your language without changes in VMs. So a great example of this might be stack switching and async. So for example, Go in async primarily uses stack switching where they kind of hop off between stacks for Go routines, things like that. Whereas Rust, for example, has a much different async model, which is more based on sort of coroutines, more like state machines-ish style things. And the idea there is that the high-level feature of async is built in Rust in a way that runs today on WebAssembly, whereas in Go, WebAssembly does not currently have native stack switching, so it is not easy to implement. So if you can change your entire language implementation to run with WebAssembly today, that's always possible, in the sense that WebAssembly is a Turing machine, but that's not exactly a great comparison. So more or less, though, it ends up being that if your native language runtime relies on a feature that's not in WebAssembly, more often than not, it's a little bit too difficult to work around. So you kind of have to get the feature into upstream WebAssembly. Stack switching is a great example where stack switching is moving along in the standardization process. And so stack switching will be part of WebAssembly eventually. And that is intended of TinyGo, and Go will start using stack switching as opposed to what they currently do today. Next question you had was, do we only start executing after downloading the complete binary or execute instructions as they are downloaded? This is one where you will still have to, you can sort of download on the fly, but you can't actually execute anything until you've downloaded the entire module. This is where there are very strict validation criteria about the module, and so you don't know that it's actually ready and valid until you have the whole thing. Once you have the whole thing and you know it's all valid, you're ready to go. However, in the out-of-browser use case, sort of not part of a browser, it is far more common that you will pre-compile everything. So you'll get your WebAssembly module, pre-compile it so you don't have to recompile it every time, and then you distribute the compiled artifact to your various servers. So that's far more common. It's the web browser use case, which is more like streaming compiles and things like that. So Wasm Time, for example, does not support a streaming compilation style. It's more intended for you either give me Wasm and I run it, which means I compile it right there, or you give me a pre-compiled Wasm, which you previously compiled elsewhere, and I will run it right there. And the final question is, for cross-instance communication without serialization, is WebAssembly passing some kind of encoded data as input for the function? Yes, I guess I would describe this as, you could sort of think of it as sort of JSON-like. It's just not JSON. So WebAssembly at the core layer I was showing you has these integers. So function parameters are I32, F32, I64, and they also have linear memory, which is just a giant blob of bytes, which is effectively your address space. So the communication there is I need to invoke a function in WebAssembly, which I'm going to pass some integers, and I'm also going to fill out some memory. But there's a lot of details in like, how do I get that memory in there? Where do I put it in the memory? Which integers do I pass? And so that's like, I guess what I'm describing is that's the fundamental primitive that you must call in WebAssembly, which is integers in memory. And the component model is sort of a way on top to say, as a host, I'm going to give you a string. And then the component model is like, okay, well, I know how to turn that into integers in memory. So it's sort of one layer removed from those very low level details. And then you get sort of the higher level, I'm passing these discrete things. There's obviously nothing preventing you from using JSON. So you can pass a JSON argument. It gets passed in as a giant string and deserialized inside the guest. You could also say that the JSON blob kind of represents, you deserialize a couple of arguments and pass those as well. So JSON can be seen as sort of the serialization can be a little bit higher level, a little bit lower level as well. But from the cross-component communication, this is where when you're in a language and you want to call a function with a string, you probably like you're not pre-serialized to JSON. You've already got your string right there. And so by crossing over to another boundary, that's where you know it's already a string. You don't have to go through JSON, so you can just copy the memory directly, and you know it's already a string ahead of time. So no extra serialization needed, but only fundamental data representation. Yeah, that's how I would describe it. The general ABI is intended to be somewhat flexible, but it's more of that you will still have to sort of marshal your sort of native data types depending on how fancy your data type is. So a string you probably don't have to marshal, but like a list of strings with records and all that, you probably do have to marshal into the ABI of the component, and then that gets transferred as is. I guess one of the major things is that as the host, which is interposing and saying, you gave me this big structured piece of data, and I want to pass it over here, the host can much more quickly walk over that and transfer it than it can deserialize a bunch of JSON and then send it over there and have you serialize, you validate, you deserialize. It's kind of a much more lighter weight operation. Those copies. So this is where components right now are entirely separate address spaces. So they don't live in the same address space. They have different linear memories. So they're required to copy memory between the two. Because if I pass through a pointer to it's kind of like if I do an RPC call, it doesn't make sense to pass through a pointer because it's in my address space. So it's similar in that regard to kind of the idea is you're copying memory across.
Sorry, just want to insert here, if you have more questions, we can postpone that to the end of the presentation. So I want to make sure Alex has enough time to finish your talk here.
That's a good point. And I'll go ahead and move on. So I think I'll talk to get to kind of the hypervisor side of things. So I'm going to list 3 downsides here, which I'll go over again here for WebAssembly. So I want to briefly go over these and say sort of some counterexamples to this, or sort of to kind of give you a bit of hope for WebAssembly as it may be. But libraries don't compile. That's definitely true. You'll have to have a lot of porting things. But as I was saying earlier, it is highly likely that the upstream authors are very willing to take patches, and it's also relatively likely that you're not the only one who's interested in getting Wasm support in a library upstream. So that's sort of very derivative of the fact that WebAssembly is a formal standard by a large number of people. It's not just one company or one person. So that really helps the community involvement, the community support for WebAssembly, and kind of making that a bit easier than it otherwise might be, although it is still a roadblock to run into. this other aspect of the CPU instructions, extra SIMD things, fancy SIMD instructions. This is one where it's a difficult process to change the WebAssembly standard, but it has happened. We've added SIMD, stack switching has been added, exception handling has been added, garbage collection has been added, various aspects there. And so this is all, it needs to be balanced with how complex is it for both producer tool chains and engines and web browsers and all that fun stuff. So a lot of stuff to balance there. It's not an easy thing to do, but it is something that's happening. Sort of as this widely agreed upon standard, you're not the only one who's interested in pushing this forward. But this last part, WebAssembly is a brand new technology, not exactly as trusted as many others per se. I want to talk specifically about that within the context of hypervisors. So this is sort of the context of we've got these battle-tested technology for virtual machines for running purely untrusted code, and I'm trying to say that WebAssembly is great. However, WebAssembly is brand new, and you have no reason to trust me. So I want to try and give you a reason to use the best of both worlds in this regard. So question of what do you think about Wasm and AI? Do you see any interesting use cases? I think I'm probably the wrong person to answer that question. I'm not a huge AI kind of deeply embedded in that myself, but what I can offer is there is WASI proposals to sort of have Wasm orchestrate AI. So like kind of orchestrate a prompt, I believe, orchestrate kind of how the models are run. You probably won't see models running inside of WebAssembly anytime soon. So WebAssembly is not going to necessarily run on a GPU and do all that fun stuff, but maybe that's sort of like the orchestration around that. But I think it still has yet to be seen how much that takes off. But there's a WASI NN proposal, and I would highly recommend taking a look at that and engaging with folks there. Yes, and then the next thing is, will there be something similar to protobuf and gRPC in the future for WebAssembly for cross-instance and same diff server runtime, all that good stuff? Sorry, yes. This is one where you certainly can run gRPC and protobuf today. We'll need to sort of build a little bit yourself, but the idea is there's also, I believe, the idea of WRPC, which is effectively components. So taking the type language of components and putting that across RPC instances across things. Yeah. So, all right, hypervisors. WebAssembly is a brand new technology. It is provably sound, and we don't have a reason to necessarily doubt that. But as I've been saying, your engine probably has bugs, just like your hypervisor probably has bugs. So we can't say that just because Wasm is provably sound, I'm guaranteed to run safe code, untrusted code safely. You could also run requirements of your organization is a very large organization. It generally requires virtual machines for a security boundary. You probably don't want to be the person to try and convince everyone to use WebAssembly instead. That's a long uphill battle and will take quite some time and will probably take a lot of buy-in as opposed to just one person. And this is also, people have been hammering on virtual machines for decades, have been trying to exploit them, have been trying to take advantage of them. Not so much Wasm. Wasm is relatively new. A lot of these sort of attack vectors, a lot of the sort of kind of mitigations, what we can do are a little less well understood. So what I want to talk here is to kind of paint a picture of, can we sort of fuse these together in a way that preserves all the good stuff about WebAssembly and doesn't pick up all of the kind of downsides of the virtual machine side of things. So to give you a brief overview of hypervisors today, I'll also caveat this with the sense of I'm not an expert on hypervisors. This is a description of KVM in Linux, and I am not an expert on that either, but at least my own personal understanding. So yeah, feel free to correct me. But in Linux, you have your host kernel. That's all running Linux. You can have a bunch of host processes on top of that. And a lot of folks today will decide to run a virtual machine inside of a process. This is run, for example, if you run QEMU on the command line with KVM, this is what's going to happen. You have one process of QEMU, and it's going to run one virtual machine inside there. The way this all works is that the host process has some code. It's kind of this little green box, and that talks to the kernel with hypervisor APIs. That's typically KVM on the Linux side of things. And that's used to manage the virtual machine, kind of get the virtual machine set up, communicate with the virtual machine, handle all that fun stuff. And then inside this virtual machine, we've got our guest kernel, which might also be Linux, and then a whole bunch of guest processes. And so this is just sort of how hypervisors work today in terms of you've got your host process, you've got your virtual machine typically per process, and the host on Linux is actually orchestrating a lot of this fun stuff. So this is all hidden from you if you're the virtual machine. You think you're just running on the hardware, and that all works all fine and dandy. But there's not necessarily any reason we have to be beholden to this particular paradigm. We could say, for example, in running this process, I would like to still run a hypervisor, but I'm going to start customizing all this. I'm going to kind of interact with KVM my own ways. I'm going to interact and kind of change this green box as I see fit. And I'm going to run a whole bunch of virtual machines. KVM supports I can have lots of virtual machines inside of one process, and they're still all separate. They still have the exact same security properties and boundaries from each other, just all in one process. And I can run a very, very small kernel and a very, very small host inside of all these virtual machines. And so this is sort of the theory of like, if we can get this working, we could probably fit WebAssembly inside these virtual machines, and we can fit it very nicely in there. But we get all the nice benefits of if you have complete arbitrary code execution inside of a virtual machine, it's fine. It's just like the virtual machine before. You're no worse off than you previously were. And you, in theory, this is sort of a defense in depth kind of thing where you already have to escape the Wasm sandbox, then you have to escape the virtual machine sandbox, then you have to escape. So this is where I get to pose the fun questions of can we actually take a Wasm engine and run it inside of a little tiny virtual machine? That's not exactly easy because we don't want a brand new Linux userland. I don't want to just run it inside of a Linux virtual machine. I want a slimmed down, very fast to boot, all that fun stuff. But I want to get kind of the same benefits as before. I was saying we can run thousands of Wasm instances of process. Can we also get thousands of virtual machines inside of one process with similar-ish overhead? And it turns out that WASI-P2 is perfect for this use case. I was saying that the component model assumes that these components are in different address spaces. That is hugely beneficial for communicating with the outside world because we don't have to deal with like these weird ABIs and syscall ABIs trying to like figure out what pointer is used where and things like that. We have a very clearly defined boundary for how these little tiny virtual machines are going to communicate with the outside world. And so we can put on top of that, we can like put a gRPC, send that over somewhere else. We can put it on the host somewhere else. We can put it on its own virtual machine. So it's kind of looking like we can solve these things. So we can strip down our embedding. We're not going to use a Linux userland. We're going to use a nice custom kernel. We're going to use a very slim version of Wasm time, and that'll all fit in a very small virtual machine in that regard. We can also, I'll briefly touch on this, but we can have a kind of a fun idea where you start a virtual machine and then use that as a snapshot for future instances of that virtual machine. So for example, if you have one HTTP instance, one Wasm instance per HTTP request, you can actually have one virtual machine all based on the same original virtual machine over and over and over again, very fast to start. And then because these are so small, we can actually pack all these in one machine without a whole lot of worry as well. So to sort of give you a bit of a diagram, the idea here is that we still have our same host process, but the host process only has little bits of the Wasm engine. It doesn't actually have the entire Wasm engine because it's not running Wasm. This is where the custom build Wasm time inside the virtual machine, that's where all the Wasm is running. That's where everything is running. And we have our own little custom kernel on the bottom managing all that. Question of does Wasm have snapshot support? Not currently based on your run. Well, it's nuanced. So actually, sort of yes. I am not aware of a runtime where you can take currently executing Wasm and snapshot it and move it somewhere else. I am aware of Wasm runtimes where you can, if the WebAssembly execution has completed, you can then snapshot the current state, throw it away, and then bring it back up for speed later. So sort of not like a live migration right of VMs just yet. So the idea here is that with this little tiny Wasm time, this little tiny kernel, we actually talk to the outside world with WASI-P2. And so this is sort of arbitrating, and then we as the host on the outside get to decide what exactly happens here. Is it talking to the actual host file system? Is it talking to other network services? Is it talking to another virtual machine? We get to be the ones that kind of arbitrate all those APIs. We get to just kind of forward things between here and there. And then these are all very, very slim and very, very small. So they get to pack tons of these on one machine, and we can actually end up running thousands of Wasm time virtual machines that are all customized to run one WebAssembly instance, do it as long as it needs, and then tear it down completely. And then it has sort of the benefits I was saying earlier of a lot of these can be mapped to other instances kind of, and that you have very few things, or like the actual resident memory is not blown up like per instance. It's kind of the per instance cost is much smaller than you might expect. So I've been saying a little bit about this kind of virtual machine stuff, but this is where you get to do little fun things with like the snapshots. Everything is mapped read-only to it, and then you have copy on write where whenever you hit it, you copy it elsewhere. But it means you can preserve the exact same resident memory across every single virtual machine. So your WebAssembly module is actually only resident in the host's physical memory once, and it is mapped at the thousands of virtual machines at thousands of different places, and it all works out just fine. You only ever actually pay the memory cost for it once. Um, let's see. Uh, I will say that this is not necessarily a panacea. There are some downsides. Oh, actually, I'll get to that in just a second. But the communication aspect is very, very nice. With WASI-P2, we have very clearly delineated host aspects of what runs where, how are you actually communicating with the outside world. You have a very nice granularity. If you can put more of it inside of a virtual machine, if it's performance critical, you can take it outside of a virtual machine if it's not performance critical. Very, very flexible there in terms of exactly how this is all illustrated. And then finally, this kind of arbitrary initialization, you can imagine doing any sort of GC startup in your own language runtime, any sort of your own personal runtime, compile regular expressions, all that fun stuff. And that can all be done in memory, and you don't have to worry about, and then you don't have to worry about all feature executions, don't have to run that. So in that sense, it's a bit of a snapshot in that regard. But yeah, Osaka.
So it looks like you're using YCP2 as the host guest boundary for communication, like device I/O. How does it compare in contrast to like more like standard like virtual I/O, virt I/O way?
And that's one I have not done personally a lot of benchmarks. So this is something that I have built a prototype of and have like played around with some performance numbers, but I have not gotten that far to benchmark that. My guess is it really depends on your use case. So if your app is very IO heavy, it will likely not perform quite as well. If your app is not very IO heavy and is very light on IO, it probably won't actually matter anyway. It just kind of falls out in the noise. But I have yet to get to the point to benchmark those sorts of things. So that would be an open question. Sorry, this is the last slide I've got in terms of caveats for this custom hypervisor aspect. And so this is where I've been saying hypervisor. The term hypervisor is a little loose in terms of I'm sort of programming against KVM, just the hypervisor. So I'm not necessarily the hypervisor. So I can say, for example, existing hypervisors like KVM are not necessarily optimized for tens of thousands of virtual machines in the same process. I've been hitting various performance cliffs, various little weird things of like if you're entering and exiting virtual machines very rapidly, that's not necessarily very well optimized. It kind of works better on some architectures and not others. So there's still work to be done here, I think, on the native side of things. No, nothing to say it can't be made better, but it's certainly something to be aware of. And this kind of like WebAssembly, this whole idea is a brand new technique and technology. I think it has a lot of promise in terms of it preserves a lot of the existing security boundaries that we have today with virtual machines. But I think also the scalability still needs to be proven out. The kind of one of the main reasons we were looking into this was sort of scalability, where when you have hundreds of cores on the same machine, they're all running Wasm instances. We're running at a lot of the virtual memory tricks we do were playing against us and causing performance to decrease. And so that was where a lot of this started, was by having virtual machines, we don't have to have communication between CPU cores, but we haven't quite proven this out yet. We haven't quite gotten to the point where we've seen these kind of scaling lines like cross, and the hypervisors do much better than the other ones. So, all right. Any questions? That's all I currently have, and I'm happy to chat about anything WebAssembly, WASI, Wasm-Time, hypervisor, all that fun stuff related. So, yeah, thank you so much for having me as well.
Well, thank you, Alex. That's a wonderful presentation, and it's really exciting to see like the comparison and contrast between Wasm, virtual machine, containers, and how they complete each other. I want to be like time aware. I want to be awareness of the time right now. It's already an hour since we got started, and Alex, if you have more time, we can maybe have like 10 minutes for questions.
Sure.
All right. So I'd like to open the floor to all of your questions. You can either unmute yourself and ask the question directly, or you can just type a question to the chat.
I see we have one already. I mentioned that WebAssembly is a kind of an alternative to containers and VMs. Now Docker is implementing a new container engine on top of WebAssembly. Any insights on this trend? Will this introduce extra latency? Um, I'm actually not personally super familiar with the Wasm integration of Docker. I believe the intention is it's running Wasm-Time inside of a container. As for latency, my guess is it would probably neither introduce a bunch of extra latency nor shave off a bunch of latency. My guess is it's kind of similar to I would expect it to perform relatively similar to sort of what you would see in Docker today.
Well, actually, I can give some insight to this question since I worked
Please do.
on the Wasm-Time continuation. So one of the ideas is to be able to reuse all of the containerd Docker and Kubernetes tools to deploy your Wasm containers to the registry and pull them down and execute them to the existing tools and platforms. So this is the big like we want to reuse the tools in your platforms. And does it introduce extra latency? The idea is you build this Docker container from scratch, and that's like a minimum Docker container. It's like usually just a few tens or hundreds of kilobytes. So it's like a very small container, and it layer on top of your file system really quickly. So it doesn't actually give you much latency in that regard.
Thank you. That was a much better answer.
Alex, I want to ask a question about the hypervisor topic. The idea of slamming down a virtual machine to be able to run like thousands of virtual machines, if not 10,000 in a server, it sounds like pretty much like the idea of unikernels. I don't know if you've ever heard about unikernels or library open systems, which was like very popular a few years ago. I think it's still popular right now. Yeah, do you have any thoughts on that?
Yeah, I definitely think this is very, very similar to unikernels, and the only major difference is that the intention kind of you get control with the WASI P2 interface or the kind of the WASI interfaces of how much actually goes in the kernel. So unikernels are often based on I've got my Linux application, FreeBSD or whatever, and then I just compile it against its own user space, and everything that it doesn't need is all stripped out. And it's kind of all one nice kernel executable at that point. This regard is more of you would compile a Wasm application like normal, and we as the hosts who are running these have the choice of putting all of those IO built-ins either in the virtual machine or outside the virtual machine, and there's flexibility kind of where to do. So with a unikernel, you kind of require that you have to give it like VirtIO, kind of virtual networking, things like that. But you just have a flexibility of maybe you need to do that, maybe not. So I think it's a little more flexible in that regard. It's certainly less portable in the sense of it's probably much easier to compile things with existing unikernels, whereas compiling a WASM application might require more porting aspects. But otherwise, from a high level perspective, I think they're definitely very, very similar. I think the snapshotting stuff, there's a few more possibilities that are open to you once you have like a custom kernel with the kind of custom snapshotting capabilities and kind of custom virtual memory that like the WASM engine internally can use. And the stuff we eventually want to do in terms of like various pages, page tables, and fancy things like that would be a little bit more difficult in a unikernel, I think, in the sense of uh, modifying a giant existing kernel versus modifying a smaller kernel. But I also realize if you kernels are kernels, and so modifying any kernel is not exactly the easiest thing in the world. So there's definitely neither is a silver bullet in my mind at all. I think there are definitely lots of overlap, some just like distinguishing features on the edges as well. And I see a question of why do we want to put Wasm inside of a hypervisor if it already has isolation? And that's a good question. And I will go back to this one. So the answer is it's up to you. The answer is it's kind of a technical question that needs to be evaluated on a per case basis. I don't think that if a WASM engine works for you, I don't think it's worth the overhead of running a hypervisor as well. That's kind of a lot of extra stuff, a lot of extra maintenance, more stuff to debug. But if your security requirements make it such that it's not necessary, or it's kind of you want that extra layer of security, specifically with hypervisors, kind of the battle tested boundary, that's kind of where it comes into. So it's sort of like more of the security conscious aspects as opposed to any performance or other aspects. Yeah, defense in depth.
Right. Do you have any other questions? Oh, I saw one comment.
Could I explain how hypervisor-based WASM instances communicate to each other? For example, VMs rely on VirtIO network or vSOCs. That it basically right now, I mean, I can say this is not a fully fledged project that's like stable and has dozens or thousands of users or anything like that. No, this is a prototype right now that I'm playing with that I have not quite fully finished quite just yet. So I can at least say for the time being, the way that it works is the way I've implemented it is just go straight to the host. So the host has a very strict boundary of I'm talking to the guests with Wasm, and then I'm using Wasm times host implementation for Linux of all the host APIs. So for example, if the guest wants to open a socket, it goes into the host, which then does the various current validation it does in WASI, and then it just calls the Linux syscall for opening socket. So no VirtIO, no custom lock devices or anything like that. This is all currently purely arbitrated in the embedder side. This is like, I mean, this is currently geared towards like you would be building and embedding. So you would be building and writing the software that's orchestrating all of this. So it's not more of a like options right now. And then is there any efforts to put Wasm engine inside the Linux kernel? I don't know. I am not personally aware of that. I would be a little surprised. But if you find it, please let me know because I'd be curious to take a look at that. I know folks I think have compiled Wasm engines as kernel modules, but I suspect it would be it would be an endeavor to add Wasm engine to Linux kernel itself.
It would be really hard to add Wasm engine to the Linux kernel. Like it would be really hard to add anything to the Linux kernel. But a fun fact, Linux Unix kernel starts to pick up Rust.
It's true. I look forward to see where that goes.
All right. I think that'll be the end of the day. Alex, I'd like to thank you for your presentation and thank you time and effort put into this presentation. I ask every guest speakers in the meetup this one last question, and I'll also ask you, what kind of advice would you give to junior engineers looking to advance their careers as software engineer?
Ooh. See, okay, well, my advice is don't listen to anyone else's advice. Is to take everything with a grain of salt, do your own thing. That's my personal advice. If I had to give to give actual advice, it's actually sort of the same thing. If I would do your thing, I would say find something you enjoy working on, and just kind of have fun with it. Kind of push it along, be it open source, be it private. You tend to learn a lot when you kind of try new things or kind of work with a new technology or things like that. So that's what I found has been very helpful for kind of pushing the boundaries of myself and also just kind of making it more fun to do later on.
Follow your heart
Yeah,
and do
it's a little
something you're
bit.
passionate.
I guess yeah. That's sort of what I realize that's sort of cheesy, but I don't know. The main thing that I would say is I would not necessarily follow anyone else's advice. Just because it worked for someone else does not mean it's going to work for you. So
Yeah.
yeah, which
Do not
also
follow anyone's advice itself is a very great advice.
well, it's ironic because it is advice, and you should follow that as anyway. I'm sorry.
All right. Thank you everyone, and we'll see you next week.